data flow-based optimization for the QIR programs. My presentation is in 4 parts, and in the first part, I will introduce the QIR. The name of QIR is the intermediate representation developed by the Microsoft, and it is an intermediate representation for the quantum program language. It's also a memory-based semantic IR, which means that it represents the qubits with the pointer to the registers and the qubit is the side effect of the function. We show this feature with an excerpt of the code convert from the Q-sharp to the QIR. The Q-sharp code includes 2 functions. It first allocated a qubit array with 3 qubits, then perform an H-gate on the last qubit. Then we can see how these 2 functions convert to the QIR code. Similarly, it allocates a 3 qubits qubit array, but before performing the H-gate on the qubits, it first needs to get a pointer pointing to the qubit register. Then the H-gate is observed by the side effects of the QIR H function. In our presentation, we use the prefix ABBR to indicate that the instruction is represented by our simplified representation. Such a design leads to 2 problems in optimizing the QIR code. The first is that it prevents LLVM built-in optimizations from being used in QIR code. Let's use a loop in the QIR code as an example. We can find that if first allocated a qubit array with 2 qubits, and the function array gets size return the array's length. There's a block jump statement at the end of the block 1. If the dot not, then jump to block 2, or otherwise jump to the block 1. Use LLVM use defined chain, we can trace that the dot not is obtained from the size of qubit array, the qubit dot I. However, since the size of the array is obtained from the function array size, and the implementation of this function is left to the backend hardware or the The LLVM optimizer cannot obtain the value of the array length directly. For this reason, the LLVM optimizer cannot perform the built-in loop lowering optimization. Another problem with the memory-based semantics IR is that it incurs the additional cost of the load data. We used a longer piece of code to demonstrate this. In this code, in addition to allocating a qubit array of length 3 and using a H-gate, a CNOT gate and a conjugate T-gate are added. As described earlier, a pointer to that qubit needs to be obtained before performing a quantum gate operation. And we can find that the quantum 1 actually points to the same qubits as qubit 3 and qubit 4. And that qubit 3 and qubit 4 are aliases of the qubit 1. The presence of aliases result in additional qubit loading overhead, since obviously anywhere the qubit 3 and qubit 4 needed to be used can be replaced with a qubit. Apart from that, in QIR, for quantum gates, it is necessary to generate a way to store the control qubit first. We denote this step as the ABBR array crate. Redundancy is just as likely to occur in this process. For example, the quantum circuit stored in this feature, the QIR will generate 3 identical qubit arrays to represent the control qubits that stores the qubit queue. Also, we use a QIR program for the gate decomposition as an example to introduce the realistic redundancy in QIR. This program consists of a total of 5 single synopses. So a total of 21 instructions to get the pointer of the qubit from the qubit array occur in the QIR code. Also, since there are 6 CNOT gates, So 6 control qubit arrays need to be created. That is, the ABBR array create instruction needs to be executed 6 times. In fact, only 3 ABBR get PTR instructions are actually needed to get the pointers to all the qubits in this QIR program. Similarly, since there are only 2 control qubits array in the circuit containing QS0 and QS1, so only 2 ABBR array create instructions are needed to get the control qubit array required by the program. That the QIR have significant potential for optimization. In our work, we present Dataflow-Based our methods is mainly 2 parts. The first is that we refer to the semantics of the QIR instruction in the specification and perform some of the classical computations in the optimization process, thus providing the opportunity to apply the system optimization on the QIR code. The second one is that we try to eliminate the redundant instruction in QIR programs with the alias analysis. Those of optimizations which are classified in 2 types in optimizations based on the QIR syntax include the QIR inline, QIR unroll, and QIR elimination. And also the optimizations based on the alias analysis, including QDFO load and QDFO create. We'll describe each of our optimizations next. The first optimization we introduce is QIR inline. We need this optimization is because in QIR, the function calls may need to be executed by QIR-specific methods due to the provision of an automatic generation of the controlled or the adjoint version of the operations. Specifically, the QIR generates a function table and is callable, and then calls each function in the function table with the QIR. To call the some OP, it needs to call the function the callable invoke. In such a case, even though we can semantically analyze the function it invokes, the LLVM optimizer can inline it with the function some OP. To solve this problem, in our method, we made it possible to inline at the stage of the QIR code by directly replacing the callable invoke function with the function it actually calls. All the optimization into the optimizer to be applied to the QIR code. So for the loop unrolling in QIR, we are concerned with the problem of the LLVM optimizer cannot obtain the length of the array returned by the array get size function. In our approach, we utilize the LLVM use define chain to find the instruction that allocated the qubit array. Based on this, we can length of the array directly modify the use of this length to the corresponding int value. The obtained code can be unrolled directly use the LLVM optimizer's loop unroll method. And then we design 2 methods, the QDFO load and QDFO create, to optimize the redundancy problem of the load qubits and the is generated with the existing qubits. As previously described, the qubit rolling occurs in the QIR code. In our method, we use a multi-dimensional vector to solve this problem. Specifically, we take each allocated array and collect the definition of the pointers to each loaded qubit. After that, for qubit, we replace the definition of the corresponding pointer. In this example, we use qubit 1 to replace the qubit 3 and qubit 4. After the replacement, we can eliminate the redundant instructions with the QIR DCE optimizations we designed it. After some of the optimization, there may be some unneeded instruction that returns the qubit pointers or return the array length. To handle these instructions, we designed the QIR optimization. Optimization removes the instructions whose current values are not used, as well as the remove mode does not affect the program behavior. Also, we designed the QDFO create to eliminate the redundancy of the qubit arrays that are generated from the existing qubit. In our method, we adopt a similar strategy to QDFO load by determining whether the qubits stored with each qubit array are identical, and replacing the pointers of the newly generated qubit array with corresponding previous pointer. In this example, we replace the control QS.I1 and control qubits.I2 with the control QS.I1. So we plan a workflow for our optimizations. QIR inline and QIR loop enrolling in the preprocessing phase to unfold the code, which can provide more contextual information for the optimization. After that, execute the QDFO load and QDFO create optimization to eliminate the redundant code. We use LLVM's O3 optimization in our optimization process because some of the classical optimizations, such as the inline, the loop enroll, and DCE can be reused. So to validate the effectiveness of our approach, we conduct the experiment based on the IBM quantum dataset. We evaluate the effectiveness of our optimization by measuring the reduction of the instruction on the set. Before executing our design optimization method on the QIR program, we first perform an O3 optimization on to exclude the effect of the classical optimization on the results. Results show that our method reduced the number of instructions as the number of quantum gates used in the program increased. We believe that there are two main reasons for the result. The first is that the increased proportion of quantum computation in the program provides more optimization opportunities for our method. The second is that as the number of quantum gates increase, the program generates redundant operation on the loading of qubits, and the general qubit arrays also increases. The result verify the importance and the effectiveness of our method, especially in large quantum programs with better performance. In addition to the experiment, we also work on common quantum algorithms for case studies. With 5 qubits, our optimization method provides a total of 1 inline and 9 loop enroll opportunities, reducing 83 and 8 lines of code by QDFO load and QDFO create methods, respectively. So, for conclusion, in this work, we propose and implement the QIR data flow-based optimization algorithm, the QDFO, to optimize the QIR programs. Our optimization provides opportunities for reusing of the classical optimization, as reducing some of the redundant operations in QIR. We verify the effectiveness of the methods by studying and optimizing a series of real-world QIR cases. Thank you for your attention.
Thank you very much, Junjie. So, are there questions right now? Please. Is that
okay?
Yes.
Oh, for this IBM curve that you showed that sort of flattens out at 87%, could you say something about why that curve is what we should expect? Why that it has that shape?
In fact, it's not brief because the it's a log n for the x alias, so it just look so curves. But in fact, if we use the use the common way to express this feature, it will become a straight line of the result.
Okay, is there another?
Yes,
yeah, is that clear? Or do you have a follow-up?
No, I don't even know what to ask now.
No, thank you.
No, I think, can you give it another try with the answer?
No, maybe.
Okay, okay. No worries. Okay, then we'll keep it there. Okay, and another question. Yes, there's one more.
Yes, so do your transformations only affect the classical processing, such as array sizes, indexing, and loading, and so on? Or do they also change the gates executed by the circuit? For example, do they remove redundant X gates, things like that?
No, in fact, we do not perform any of the circuit, quantum circuit optimization or optimizations. Maybe it will be our future works.
Okay, that was also my question. Good, that has been answered. Any more? Okay, then let's thank the speaker one more time.
So, thank you very much.
So that's